anyone not know Angela? I can continue. Oh, sometimes referred to as Ashley in our lab groups meetings. She loves that, by the way.
And Ashley.
Yeah. So she's been working on her PhD thesis research in Brazil, where she learned to speak Portuguese. She learned to hug strangers, which apparently you don't do in Alberta, and a range of other things.
Some Albertans do. Thanks, Mark. Yeah. No, you high-five them from a distance.
Yeah.
Hey, Mom.
All right. And just last week, she submitted a very strong paper to environmental science.
Yay. Thanks. All right. So can somebody mark the time for me here? Keep me on track. Thanks. All right. So today, like Mark said, I'm going to be, yeah, I'm taking 20. I'm going to talk to you about the year I spent in Mato Grosso, Brazil. I'm going to show you lots of pretty pictures, where I was hosted by the University UFMT doing work in the lab and the field. So my work was broadly related to the Brazilian bioethanol industry, which many of you will probably know is the largest scale and perhaps the most commercially successful biofuel scheme out there. And it's arguably the world's greenest bioethanol. And that statement is usually based on values related to the net energy return on investment, which is the amount of energy you put in for what you get out. And for sugarcane bioethanol, that's 9, which is actually quite high compared to corn bioethanol, which is around 1 to 1.5. So supposedly a very, very good green bioethanol. The downsides, however, to bioethanol and other biofuel crops is that there's some habitat and biodiversity loss. There's air quality issues seen here when they burn the sugarcane in Brazil. This is a big problem. It's recently become illegal, but still happens. There's a water pollution issue that comes specifically in sugarcane bioethanol from an effluent called vinasse, which I'm going to talk about a bit. And there's some soil degradation issues. So the last two of these are really the focus of my thesis, or at least the stuff I'm going to talk about today, because there was lots and I could only fit in a little bit. Okay, so the region that I was working is called the Cerrado biome, which is a savanna-type ecosystem. It's very beautiful. It's a lot of grasses and shrubs and really scraggly trees and a maned wolf there you can see in the center, which is very cool. This is a huge area within Brazil. It's about 200 million hectares, and 50% of that is arable and is kind of in the future broadly intended for agriculture. So the issue with this region is that the soils are extremely acidic and they have very low what we call cation exchange capacity, which means that they don't retain charged nutrients very well. They tend to leach away through the soil with rainfall really quickly. And so because of this nutrient leaching and the other stuff, this region has historically been very difficult to farm, simply because the amount of money you had to put into lime and fertilizers to make it profitable. But in recent years, it has become very profitable to farm in this region on a large scale. And because of that, 80 million hectares, or about 40%, has already been converted. And that's mostly pasture and soy, but a small but growing portion of sugarcane for bioethanol. Oh, I can just do this. That's why I have a clicker. Okay, so why do we care about conversion? The reason that I'm focusing on in my thesis, there's many reasons, of course, but for my purposes, it's that the Cerrado is surprisingly rich in carbon, okay? And that carbon is lost through the conversion process. So to put some numbers on this, above the ground in Cerrado, you have about 10 tons of carbon per hectare, which is in the form of trees and grass and jaguars, maned wolves and other cool things. The below ground biomass, which is roots and critters, is about 18 tons of C per hectare. And then the real shocker is the soil organic matter, which holds about 165 tons of carbon per hectare just to 1 meter. So these soils are actually very deep. That number could be much, much larger. The total for that is a very conservatively estimated about 190 tons of carbon per hectare, which is lost, or potentially part of it is lost. So what happens when Cerrado shifts to sugarcane? So the plot goes up for sale. Very first thing that happens is that it gets cleared by fire, okay, which means that because it's being burnt, very little of that biomass carbon is making it into forest products, so there's no kind of long-term sequestration of that carbon. It's just all released to CO2, it's gone. The next process is subsoiling and resulting decomposition. So what's happening here is very, very deep tillage to like 60 centimeters or 100 centimeters deep into the soil, which is done to decompact the soil, but also rip out all the roots. However, through the same process, it's all that soil organic matter I talked about is being exposed to light and heat and oxygen in such a way that the soil organic matter is oxidized, or at least part of it, and released to CO2. It's gone. So now we've lost some stored carbon right there, actually quite a bit. So by the time it's sugarcane is growing as very productive, but it's being subsoiled about every 5 or 6 years, so that disturbance is ongoing. So to put some numbers on this, there we go. The above ground biomass is a little bit larger than native Cerrado. However, it's harvested, so that's not a stored carbon. That's a flow that's leaving the field. Below the ground, we have much less carbon, which is in form of roots, which die every year. And finally, that soil organic matter from the studies that I've read sees a decrease around 50 to 70% in storage, for a total of only about 36 to 60 tons of C per hectare. So that difference between 193 and 60 is what we call a carbon debt. Okay, this is the amount of stored carbon that was lost just through conversion. So very clearly here, soil organic matter is being lost, and this is a very big deal. Because of this carbon debt I mentioned, it means that green biofuels aren't actually carbon neutral for X number of years until the emissions you avoided through switching from gasoline are equivalent to the amount you lost from the native system. So this is kind of an issue for greenness of biofuels. There's also obviously a climate regulation problem here. Soil organic matter actually in the world, all over the world to a depth of 1 meter, contains double the carbon that the atmosphere does. So this is not good if this is liberated on a large scale, which it already is. And so for my thesis, the big issue here was I'm not actually breathing. Just exhale. Inhale. Okay, all right. For my thesis, the interesting thing here is soil ecosystem function. So most of my thesis work is soil science. And so as I've told you, Cerrado soils are very nutrient poor, and they dry out quickly because it is extremely hot in this region. So that soil organic matter is absolutely critical to be continually replenishing the nutrients available for plants, and also to absorb and retain some water for periods, from wet periods to dry periods. Okay, so this SOM is actually very, very important. So the reason why I got really interested in sugarcane carbon cycling was that it's very dynamic. Within the field, there's a lot of carbon cycling, and that is because the harvest and processing of sugarcane actually produce very, very large amounts of organic residues, which are returned to the field. So these include things like the leaves, the roots, and the top of the plant, which are just left there, or they're burnt on the field and the ash remains there. There's a residue called bagasse, which is a fiber, which is taken to the plant and it's actually burned for electricity and heat for operations. There's this horrendously foul liquid effluent called vinasse, which is really rich in carbon and nutrients, and it's used for fertigation, which is irrigation and fertilization simultaneously. They spray it on the soil. God help you if you're on the field at that time. And finally, filter cake, which is a solid residue that's applied as a soil fertilizer. So as you can see from this list here, 3 of the 4 residues are actually going back to the field, okay, which means that overall, 30 to 60% of the carbon fixed by the sugarcane is remaining or returning to the field. Okay, so then the question becomes, why can't sugarcane store more carbon than it does? Or, at least at a level comparable to the native ecosystem when it's so productive and returning so much carbon. So this has to do with the chemical nature of carbon. As I mentioned, this environment is very, very hot and sugarcane cultivation. What do you mean? Which one? Oh, sugarcane specifically, because of this carbon input. Other crops don't have the same kind of carbon returning to the field. So, yeah, hot and humid, and because of this, soil microbes are very, very active, and they tend to decompose things very quickly. Combined with that subsoiling process that I was talking about, that continual disturbance, carbon is lost very quickly. And so what happens is the easily decomposable or labile carbon is used first, and the chemically more difficult to attack carbon, recalcitrant carbon, is left for later. Okay? The big issue that we have here with sugarcane production in particular is those residues returning to the field, the vinasse and the filter cake, are primarily labile carbons. So they are metabolized very quickly and they're gone. The carbon does not stay on the field. Okay. So one of the options here to deal with this, a possible point of intervention, is to alter the chemical nature of the carbon itself. And so this is done by taking the waste biomass and heating it in the absence of oxygen, which is pyrolysis. and it produces charcoal, which we call biochar in the literature. And it has to, or what it does essentially is it creates or converts the carbon in the biomass into a form of carbon that is very difficult for microbes to attack, supposedly. There's also other co-benefits. You get heat and syngas production if this is applied to the operations of the plant. And so the question becomes, does this biochar prevent that rapid decomposition? And does it have other positive or negative effects on the soil? So my thesis, what I did was I made some biochar at great personal risk, just kidding, it wasn't that bad, from some filter cake, and I looked at its effects on how much water is retained by the soil, its effects on nutrient availability for plants, whether or not it influences the loss of nutrients to leaching from water flowing through the soil. These soils lose a lot of nutrients to leaching. And what is the effect on decomposition? So I made my biochar, I built a reactor, which is basically just a steel tube. Those copper tubes here coming in the top, those are actually, it's a nitrogen gas flux. It just pushes through and goes right out again because I'm trying to exclude oxygen from the chamber. And then these other two things here, these are thermocouples to monitor temperature inside the reactor. So I got that made at a metal shop. And then I heated the dry filter cake at 575 for 3 hours in this N2 atmosphere. And what I got out of it was this. Doesn't look like much, it's charcoal. But the interesting things about it, its chemical properties are very different. So filter cake has a very low surface area. So surface area is the potential sorptive area of the material. And that's about 0.4 in filter cake, and it increases to 26 meters squared. 26 meters squared per gram in this material. So much more potential area for absorption. And it reduced the amount of labile carbon in the form of carbohydrates. I did get numbers on that, that's all settled now. And it increased the amount of stable or aromatic carbon. So just for like some basic soil quality testing, these are really basic kind of agronomic things that you always look for when you're talking about manipulating a field. pH, first of all, increased. This soil wasn't that acidic, but increased quite a bit with a 5% addition of biochar. This value here is the cation exchange capacity, which increased a lot, which is actually quite difficult to do. And of course, percent carbon increased because I'm adding carbon directly to the soil. And in terms of nutrients, phosphorus, potassium, calcium, and magnesium all increased. So these are all very positive things, and it's a reason to go forward. So I did many experiments. I'm just going to show you two here. The first one is one that I did on the effects of leaching. So as I mentioned to you, that vinasse, that liquid effluent, it's a really serious source of water pollution in Brazil. It's in the past more than presently, but it remains an issue. It has very high dissolved organic carbon and very high nutrient content, and it's quite acidic. So it's a big issue for aquatic ecosystems. It causes eutrophication and fish kills, but it's also a big issue for humans because, as Ashley mentioned in her seminar, when you have a lot of dissolved organic carbon in the water, you can get the formation of disinfection byproducts and potential health effects. So this is not something we want in water. Unfortunately, it is produced at very, very large quantities, about 8 to 18 liters of the effluent for every 1 liter of ethanol. So we're talking massive production of this stuff. And as a result of that, it's kind of almost inevitable that even though it's applied to the soil as a fertilizer, it's almost always overapplied, like massively leaching and running off of the field. So we looked at this and we said, okay, biochar is a charcoal, which means it's a sorbent. So can we prevent some of this leaching from happening? And what you can see here is a column experiment I set up where I have 12 soil columns. So there's 4 treatments there that are hooked up to these little vacuum collection flasks, which are then hooked up to a vacuum manifold and pump. And so there were 4 treatments represented here. And the first one is just a soil with water flowing through it. That's just kind of like a control. This is a soil column here, but with vinasse flowing through it, simulating the polluted state. This column here is receiving vinasse, but it also has some biochar on the top to see whether or not the biochar would prevent leaching. And finally, this is a column that receives water and just has biochar in it to see what the effect of biochar alone on the soil is. And so I applied these things, and then I looked at dissolved organic carbon and nitrate coming out the bottom of the column. Okay, pretty good. So what I saw was this. These 4 traces correspond to those, oh, I've got some different colors in here I didn't know about, correspond to those 4 treatments. So this line right here is just the soil by itself receiving water. So you can see there's not a lot of variation in dissolved organic carbon coming out of that column. This is over time. I'm drawing off 250 milliliters of sample and then analyzing it. And then this trace right here is when you apply vinasse. And there's a big upshoot because that vinasse contains a lot of dissolved organic carbon. Okay? However, when it's co-applied with biochar, that is significantly reduced. And when biochar is applied alone, it also retains a lot of the carbon in the column and doesn't let it escape. So what this is telling me in general is that biochar is greatly attenuating the release of dissolved organic carbon from the soil. So I actually did further experiments to this, and I found that the carbon being retained is not necessarily the carbon that's in the vinasse. It was actually the carbon that was in the soil. Okay, so you see this difference here is quite similar to this difference here. It's because they're the same. It's not actually stopping this carbon from getting through. It's stopping this carbon from escaping. So that was it was an interesting result, and that's the paper. However, it had no effect on nitrate flowing through. In fact, the biochar may have sped the flow through of nitrate, which is another really interesting result. It has to do with the porosity of the soil in the column. So the second experiment that I want to tell you about is the main thing that I've been getting to here is the decomposition issue. So in order to look at the decomposition of the carbon in the soil, 5 more minutes, I did a CO2 efflux study where I packed different treatments in these little shorty columns here. Oh, these little columns right here. Okay. And then those treatments were soil by itself, soil with the raw filter cake, which is applied to the fields, and then soil with filter cake as biochar. Okay, so this is basically just the difference between applying the filter cake to your fields or the same amount of biochar. And then I analyzed it with one of these, it's a Lycor infrared gas analyzer. Basically this thing here just plops on top, it gets sealed on there, and it measures the flux of CO2 coming off of the soil surface. So this looks intimidating, but it's not. Here on the left, these 3 traces are soil CO2 effluxes. So this lower trace here is the soil itself. It's releasing very little carbon as CO2. Here, the second trace, this is with biochar. So it's actually releasing a little bit more carbon, but not much more compared to soil. The big and obvious shocker here is the trace with filter cake in it. So this is a logarithmic scale. This difference here is about 100-fold higher than just soil or biochar alone. Okay, it's a very, very big difference. Within the same experiment, I also applied different liquids. So the black line here, this is, you got your soil alone, and at this point here, I applied some vinasse, which did cause a little bit of increase in the amount of CO2 released in soil with biochar, and in soil with filter cake. It had no difference, simply because this system here is already respiring, producing CO2 as hard as it can. It can't be made to produce any more through applying vinasse. So basically, vinasse did have a very big effect, but this effect between raw filter cake and biochar was very large. So the results from this are that relative to the initial amount of carbon that I applied, the vinasse had very little effect. The biochar treatment caused a small but significant effect, which was probably due to decreased density or increased aeration of the column, or possibly a priming effect. And finally, the raw filter cake led to this huge increase in percent C lost. So the conclusions from my thesis are going to be, in addition to other things, that this biochar, applying at least some portion of the residues of biochar, may help to build soil organic matter in sugarcane fields. It may help to improve soil quality and decrease those carbon losses to both leaching and decomposition. And in stuff that I didn't show you, it was shown to increase water held in soil that's available for plants. It affected the portion of carbon that was being utilized in different soils, and it also prevented leaching losses of other nutrients. So this was all very positive. I'm hoping to get 3 to 4 papers out of this stuff. So I owe a lot of thanks to a lot of people. My Eco-Hydro lab group, well, those are cows. Not cows, not cows. That was not a commentary. My Eco-Hydro lab group, which is headed by Mark, my committee members, Hadia's on my committee. Ashley helped me a lot with stuff I didn't show you today, but I'm taking the chance to thank her. In UFMT, I had 3 profs, Eduardo Couto, Ricardo Amorum, and Shiko Lobo. I spelled his name wrong, that's terrible. But they provide me with a lot of resources in lab space. This guy right here, this happy guy, is my Ejimar. He's my lab assistant who did a lot of like the on-the-ground work. Great guy. And then all these other people are people from the field that allowed me to tag on to their expeditions and go have fun with them in the wild Sahara. So funding from UBC Bridge, because I do have a bridge connection, and NSERC, and also CNPK. Questions? Yes. All right, go for it, Hedy. No? What? I was waiting for you. Okay, go for it. Yeah. Of what? Clay? Yes. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Yep. Clay is very, very heavy. Very heavy. Clay is heavy. To actually amend these soils in the same way you would with biochar would be very expensive to haul that clay in. And so this biochar is something that comes from the field. It could potentially be made on site in the plant in the same way that they have like a little cogen facility to burn the bagasse. They could, I'm not an engineer, so I'm not making any claims, but they could with some facility switch that cogen facility to a pyrolysis facility and be making this biochar on site, which would reduce transportation costs from mining and spreading clay. But well, I think that would still be a cost, though. Here on a sugarcane plantation, this filter cake is a really big nuisance, so they have to actually pay to get rid of it. They have to pay to ship it away. Okay, so if they were to pyrolyze it on plant and potentially get syngas and heat out of it to reduce their costs in other senses or sell it back to the grid, they'd actually be making money off of this rather than spending money. But you make a good point. This biochar actually has the same cation exchange capacity and surface area that the local clay does. So it's basically like augmenting the clay fraction of the soil. Yeah. Yeah, it did. Mm-hmm. That's a big problem on this plant, to be honest. That's my next one. Justin? Justin. That's it was actually really, really difficult. It's because every biochar is different. Every biochar and soil combination is different. So the biochar, there's really a lot of variability depending on the feedstock you use and the different pyrolysis conditions. So what I did was I did a really exhaustive literature search focusing just on biochar made from bagasse. And I tried, because bagasse is most similar to filter cake, and I tried to pick out a program that was going to give me like a certain characteristics, high sorptive material, highly sorptive, high carbon retention, all these things. It didn't actually work out as well as I wanted to do. I was trying to get a material with a much higher surface area, but besides that, I achieved all the other parameters. So it was a very focused, purposeful decision, like how I made the biochar specifically, but it was a new feedstock, so it was a little bit difficult. Sure. I characterized the biochar itself really well, but I didn't have the time to do like different programs. It just wasn't, I had the muffle furnace in somebody's lab for exactly 10 days before they were going to shut it down and kick me out for 3 months. So with activated charcoal, that's a totally different field because there's other post-processing things that go in there, but that can be as high as 700 meters square per gram, okay? So bagasse biochar that's made at the same temperature and conditions is usually around 200 meters square per gram, and that's what I was aiming for. However, it wasn't possible simply because I think this filter cake has been ground and crushed and then fermented and then filtered, so a lot of the vascular structure inside the plant has been destroyed, which is the basis of a lot of the large surface areas in these other materials. So it wasn't necessarily going to hit that point, but I still think it did pretty good. Terrific.
Sort of a broader question. In your outline, why this landscape is challenging for agriculture and expensive, and then that sort of shifted and now it's profitable to sell these here and that whole thing. Is that really economic demand for biofuels increased, or are there other factors?
It's actually mostly soy, and that's not even true. It's actually mostly pasture. It's mostly beef farming in this region, but the reason why I don't discount these other forms of agriculture is because that something like 40 million hectares of pasture, which has now become very, very degraded over time from just overuse. And so recently there was an agroecological zoning framework that was put out by the Brazilian government that's kind of like trying to steer biofuel development in the future. And so one of the regions they're steering it onto is the Cerrado because of all these degraded rangelands, which are going to be a really, sugarcane will grow in sand if you put enough product on the surface. And so the idea here is they're going to be, the Cerrado has been converted, and now some portion of that land is being laid to waste, and in the future they're hoping to use it for sugarcane. So this is a way that they might actually be able to get something out of for sugarcane, and hopefully not have to chip away at other regions that are still pristine. But that doesn't actually work in practice. Yep. Mm-hmm. Yes, because they're actually applying it to a fallow field. There's no sugarcane planted on it yet, and yeah, it tends to. They apply so much that it just runs off in rivers. The only criterion that is used for deciding where and when to apply the vinasse is where it's convenient. So because of the expense of canal and pumping systems, it's mostly applied close to the distillery, which is also close to the river. So most of the application is happening within like 2 kilometers of the river. And yeah, they have crews that move the pipes and the big sprayers, and they just spray as much as they possibly can until it's completely saturated, and then they move up to the next section. So there's no management of the vinasse, basically. That's it. Okay. Thank you.